Hi, my name is Stanton, and I'm from West Texas A&M University. And for my legacy project, I'm going to be doing problem 4.2, chapter 4, which is electric fields and matter, and you can find that on page 160 if you want to follow along. And specifically, boundary value problems with linear dielectrics. And main note about dielectrics, the electrons can only move slightly within the atom or molecule, not throughout the entire material, which makes them a special case. So problem 4.22 is on page 190, and you can follow along in the text. A very long cylinder of linear dielectric material is placed in an otherwise uniform electric field E naught. Find the resulting field within the cylinder. The radius is A, susceptibility XE, and the axis is perpendicular to E naught. So to start off with this problem, we're going to write out the boundary equations, the boundary conditions, and there's three of them. Those are the boundary conditions. So we'll zoom in a little bit. So with these boundary conditions, first we need to find the V functions for in and out. And the basic equation is from chapter 3 on page 139, equation 3.65. And again, these equations were introduced in chapter 3. So for the potential in, the V term will cancel out to avoid blowing up at the origin. And for the out, same rule applies, and the A first term will cancel out. So I'm going to go ahead and switch it over to, you want to convert it to symmetrical cylinder or symmetrical cylinder and cylindrical coordinates. So I'm going to go ahead and write the V in and V out in cylindrical coordinates. These are our two potential functions for in and out. So based on our boundary conditions, the first thing we want to do is set um, v in equal to v out. So that's the equation adding them all together. If we go back to the second boundary condition, we need to take the partial of Vn, which is this portion, with respect to r, which in this case, since we converted it to cylindrical coordinates, it will be with respect to s. And then times e in the other side, we'll take the partial with respect to s and multiply by e naught. I'm going to go ahead and erase some of this so we can have room on the board. So we're doing the second boundary condition and taking the partials of each side of setting v in equal to v out. Okay, so that's v in. And we're going to do v out now. So now once we take the partials of everything and we'll put them equal together now. I ran out of room, so I wrote them separately. So I'll put them together, and after taking the partial, this is what you'll get. And just to save some time, we're going to go ahead and write this in here. It's the same equation. So once we have that, we want to divide everything by A naught. And E over E naught is equal to, I guess, epsilon over epsilon naught is equal to ER. So this term is now epsilon R, and that is equation 4.34 in the Griffith text. So once we apply that, this is epsilon naught R, and these epsilon naught values disappear. So this is what we're left with. Now we're going to set the constants dk and dk, the constants that are in front of the sine k phi, equal to each other and equal to 0, as well as ak and ck, the constants in front of the cosine k phi, equal to 0. And so, and then k equals 1. So once we do that, these are the only things that satisfy the conditions for this case. So now we're going to go ahead and put, we're going to set the bk's and the dk's equal to 0, and the k equal to 1. So when we do that, bk equals to 0, that cancels out the entire term. And same over here with the dk term. And remember, we're using this this section plugged in for this equation right here because I ran out of room. So now that we have that, we're going to go ahead and write out setting the k values equal to 1, and you get epsilon r ak cosine phi equals negative e naught cosine phi minus s to the negative 2, and then ck cosine phi. And now we're going to solve this, condense it and move it around a little bit. And when you move it around, you get epsilon r ak equals negative e naught minus s to the negative 2, and then ck. So, and remember that we're going to change these s's to a's. It states in the problem that our radius is a. So I'm going to go ahead and change that to a. So now, similarly with the other satisfying conditions, here we're also going to get an equation doing the same process. That would come out to be a, which is our s, the radius, ak equals negative e naught a minus a to the negative 2, sorry, I was writing the other equation. E to the -1 and ck. So with these two equations, we're going to want to set, we're going to solve for ak of each of these equations, set them equal to each other so we can find the value for ck. So I'm going to erase this and I'll start at the top. And these are the two equations that we're rearranging. So when we rearrange, we'll go ahead and go through the example, setting everything equal to ak and then solving for ck. And that's the first equation. And since we set that we're solving both of them for ak, we're going to set them equal to each other. And when you move it around and try to solve for ck, because now that this ak is gone, they're both equal to ak, so these two equations are equal to each other, and we're going to solve for ck. And after you rearrange that to get ck, this is what you're going to get. And then similarly, we do the same thing. We set everything equal to ck and then solve for ak. And we're not going to go through that because we just went through the process. It's going to be the same process. And when you set those ck's equal to each other and condense down to find what ak is, you're going to get this. Okay, so now that we have our ck and our ak, we want to plug them back into the potential going in. So again, we're going to refresh our minds with the potential in equation. Remember, this a is because our radius equals a. It's not the constant that we did. That's a raised to the k, and the constant is just a, so script k multiplied by ak cosine k phi plus bk phi k phi. And remember, we set our bk's and our dk's equal to 0 when we came up with the equations for these. So since our bk equals 0, it cancels out this term. And you're left with, I guess we have to rewrite it. This is what we're left with. And then we're going to plug in our ak value into our equation. So ak was -2 e naught over 1 plus epsilon r. And remember, k equals 1. So a to the 1 is a, and that's our radius, times cosine k, which equals 1, times cosine phi. And since a cosine phi equals x, going to change this, our Vn. So A cosine phi equals x. We get rid of those terms and substitute the x in. And the question asks for the remaining field. So in order to solve for field, it comes from this equation here, and it's the potential is equal to the integral E dot dl. So in return, since we're looking for E inside in cylindrical coordinates is going to equal negative partial of E in with respect to x. So now that we have that, we just plug in our V in, which is here. So E equals the negative partial with respect to x of negative 2 epsilon naught over 1 plus, or 2 E naught over 1 plus epsilon r times x. And since we're taking the derivative with respect to x, that's just going to come out to, and these two negatives cancel, and 2 E naught over 1 plus ER, and that's the constant that's in front of the x when you take the partial. So this is our field that is left, and to simplify it earlier, we said that susceptibility is xe, that's stated in the problem, so we're going to use equation 4.43 again, and that states that epsilon r equals to 1 plus xe. So when we substitute that in for our ER, our final E is going to equal 2 E naught over 2 plus susceptibility. And that is the resulting field within the cylinder. Thank you.